In this section, section 10.3, we're going to start to look at some of the theorems that will enable us to determine whether a given infinite series converges or diverges. With each new theorem that we encounter, we have to not only try to understand what that theorem tells us, but we also have to identify properties of a series that indicate when that theorem is appropriate. So we've referred to this over and over again in class as triage. And so every time we work through a new theorem, we want to think about how we identify properties of the series which indicate if that theorem or that convergence test is appropriate. First one we're going to discuss right now is pretty intuitive, and it kind of hinges on the relationship that we've seen already, that some sequences can be translated into functions of one real variable. So if you remember back at section 10.1, 10.2, I defined this sort of stupid word here, forvable, for sequences which can be written as a function of one real variable. Some examples, just as a reminder. Here's a couple, 1 over n squared, natural log of n over n. In all of these sequences, if I chose to just write the variable n as an x, then the resulting function is a legitimate function of one real variable. In contrast, here's some examples of sequences that are not forvable. Remember that we've talked about how if I write 1 over x factorial, if x is a real value as opposed to just an integer as n is, then that function is not defined. Similarly, if I have exponentials and I want to write them as functions of a real variable, I need my basis to be positive. So what we're going to do for this first theorem is focus on this first type. We're going to focus on forvable sequences. And I want to start by just looking at an example of such a sequence, a pretty simple one. Here we've got a sub n equals 1 over n, and the corresponding series, which is just the sum of the terms of that sequence. And I kind of want to just think about what exactly this series is trying to do. First of all, since this is forvable, I know that I can rewrite this as f of x equals 1 over x. And I've graphed f of x equals 1 over x here. So f of x equals 1 over x is the continuous function where I use as inputs all real values. So I use as the values, say, 1.5 and 1.25, and actually all of the real numbers between 0 and 1 are used as inputs. The sequence, in contrast, is just evaluated at positive integers. So I'm just inputting things like n equals positive 1, n equals positive 2, etc. On the graph, that corresponds to just evaluating the functions here at positive integer values. So it's like I'm just evaluating that point right there. I'm just evaluating it at n equals 2, so I'm just getting that point right there. At n equals 3, etc. And I'm not collecting or evaluating or summing any of the intermediate values. I'm just getting these values here at these integer points. But if you think about trying to add up that value plus that value, actually draw that in. That'd be like adding up this height. Okay, pretend like that's straight. I'm adding up this value, which would correspond to this height, the height of that line, the height of this line, etc. And then this series is asking me to add up those heights indefinitely. So as the index continues to grow without bound. So adding up the height of a function over and over and over, it kind of feels familiar. It kind of feels like we're doing an integral. But if we formalize this, we get a pretty powerful theorem. And so let's kind of clarify those details. Just backing up, the takeaway from that example is that when a sequence is forvable, and then has some additional properties that we'll identify in a sec, then the behavior of the corresponding series is the same as the behavior of the associated improper integral. Remind you that this doesn't work in all cases, so part of my triage is that I have to determine if my sequence is forvable and has the corresponding properties, the additional properties that we'll point out. But if that's the case, then I can apply this theorem. So here's a formal statement of the theorem. We call this the integral test, and it says if f is, there's 3 important properties here. The function needs to be continuous, It needs to be positive. It needs to be decreasing from x equals 1 to infinity. And if we want to suppose that there is this the equality between our function and the sequence when we evaluate the function on positive integers, then the series will converge if and only if the corresponding improper integral also converges. This if and only if is significant. Remember our converse contrapositive. This is telling me that it works in both directions. So if I can determine that this converges, that tells me that my series converges. Similarly, if I can determine that this integral diverges, that tells me that the corresponding series diverges. So let's give it a shot. This is the same series that we were dealing with a second ago. Let's go ahead and formally determine whether it converges or diverges. First thing I'm going to do is I'm going to translate this into the corresponding improper integral. And then let me actually go through the details of evaluating this integral. Integral of 1 over x is natural log of x, because I don't need the absolute value since we're only dealing with positive x's. Too late. And if I want to evaluate that, we remember that we introduce a limit to accommodate that upper bound. Over here, I'll plug in my lower bound. And this value does in fact equal 0, but this value grows without bound, goes off to infinity. And so the overall value of this limit will be a positive value that grows without bound. So applying the integral test, the corresponding infinite series, which we started with, will also diverge. Let's try it again. This was when we were doing improper integrals. This was kind of the other example that we relied on a lot. So this is going to translate to the integral from 1 to infinity, 1 over x squared dx. Let me take a second to evaluate that. Now this portion here, when we evaluate this limit, we know that this limit goes to 0. So the overall expression of my integral, the overall value of my integral is 0 plus 1. So what's important to take away from this is that this improper integral converges. So by the integral test, the series 1 over n squared also converges. It's important to note that the theorem indicates whether the series will converge or diverge, but it does not indicate what value the series is converging to. So in this previous example, we saw that the integral has a value of 1. We know that the integral converges to the number 1, but the theorem doesn't tell us how to determine what value the series converges to. Let me summarize that quick. So now that we've got a sense of how the integral test works, let's try one more example. Let's try to determine the convergence or divergence of the series, or my sequence is n e to the negative n. First, I'm going to convert this to the associated improper integral. And now to evaluate this integral, I recognize that I have to use integration by parts. So now on this first part, in order to evaluate this limit, I have on the second term, that's definitely going to go to 0. This first term, I've technically got a L'Hopital's going on, but it's going to also go to 0 as well. So both of those terms will go to 0. That leaves this second term. Got to do a little bit of simplification on this. So my final value for the integral is 2 over e, but what I really care about is that this integral converges. So my conclusion will be that the corresponding series that we started with also converges.